Let's understand exponential functions. Okay, after all, what is it? You have seen like y equals to 2 to the power of x, where x is in the exponent. Let me give you one example of an exponential function. A function of this form, f of x is equals to b to the power of x in general, is called an exponential function. B to the power of x, where b is a number and x is the variable. Notice here that x, the variable, is in the exponent, okay, not here. It is not 5 square, okay, it is not x square. On the top, exponent is a variable, okay. So where x is a variable which belongs to set of real numbers, okay, and b is the base, and b has some restrictions. B should be greater than 0 and b should not be equal to 1. Do you know why? We'll answer these questions soon. Okay, both these questions. Now, let me just check with you one thing. Is 2 to the power of 5 an exponential function? No, it is not. Why? Because exponent is not a variable, okay? Okay, is x square an exponential function? No, it is not, since variable is here but not in the exponent, okay? So these are not exponential. Do you understand? So this is something which you have to keep in mind. For exponential function, we should have at least one variable in exponent. So that's the base, okay? Now, let's try to sketch some exponential function and get an idea of how do they look like. So let me draw the x's here like this. Okay, and we'll make some table of values and then plot them here. Let's say, let's start with simple function like 2 to the power of x. So, and let this be x values. If x is less than 0, then 2 to the power of 0 is how much? 2 to the power of 0, or any number to the power of 0, is 1. Correct. If x is 1, then 2 to the power of 1 is 2. How about x is 2? If x is 2, then 2 to the power of 2 is 4. So we get these values. Now let's try some negative values for x. If I write negative 1, what does it mean? It means 2 to the power of negative 1. Let me explain you here. 2 to the power of negative 1, which is equal to what? Which is equals to 1 over 2. Correct? If I write negative 2, then it will mean 2 to the power of negative 2, which means what? 1 over 2 square. And what is 2 square? 1 over 2 square is 4. So we get this. So it's like reciprocal of these values. Do you see? For 1 and minus 1, we get the reciprocal value. For 2 and minus 2, we do get the reciprocal value. That is the meaning of when we have a negative exponent, it makes the number reciprocal. Correct? Okay. Now, if we have to plot these values here, let's take on x-axis 1, 2. Let's say this is my 1. And let's say this is my 2. Let me just write here more divisions. Here I have minus 1 and here I have minus 2. This goes on like this, right? So there's x positive and here we have f of x. Now we want to go up to 4. So let me say, let this be 1 for me, 2, 3, 4. Okay. Now let's say this is 1 for me. Let's plot these values here. So at 0 we have 1. I like to start with 0, so we will move both sides. At 1 we have 2. So at 1 the value is 2. Is here. Okay. At 2 it is 4. So it's 2, 3 and 4. So we go up like this and get a value. Okay. Now at minus 1 it is half. So half will be kind of here. At minus 2 it is 1/4. This comes very close to this. Imagine. If it is minus 3 it will be even half for this. So let me go. So as we move this side, we are, do you see, approaching the line. We'll not ever reach it. We'll never reach x-axis. It will be slightly more than 0. Howsoever, even if you go millionth time, so it will be 1 over million, but never 0, right? Very, very close to 0, right? We also say, since we will write like this, since as we approach to a very large number, let's say negative infinity, right? Then how does our function vary? Function approaches 0, but from positive side. Do you see that? And so we call this as a horizontal asymptote. So horizontal asymptote for us is y equals to 0. So as x approaches a negatively large value, we approach y equals to 0, the x-axis. Okay, that's the origin. So if I connect all these points, I get my graph for 2 to the power of x. Like this. So that's my graph for 2 to the power of x. Now, on the same scale, let me draw 3 to the power of x. Now, without sketching, can you tell me how will it look like? So we'll write again x values, and this time 3 to the power of x. So for 0, 3 to the power of 0 is 1, right? And for 1, it will be 3. 3 to the power of 1 will be 3. And for 2, it will be 3 to the power of 2, 3 square, which is 9. And for minus 1, we'll get reciprocal of this, 1 over 3. For minus 2, we'll get 1 over 9, 1 over 3 square. Correct? So you will observe that when I draw 3, we have same y-intercept. Y-intercept is always 1 for our base function, right? Okay. But at 1, the value is 3, not 1, not 2 as it was in the case of 2, but 3. So it's higher. Do you see that? And at 2, it is 9. So we are only here to 4. 9 will be like somewhere there, okay? So it's much, much steeper. Do you see that? But what about negative values? When the exponent is negative 1, it is 1/3. This was half, right? This is much lower than this. So this part of the graph, you will see, is like under the 2 to the power of x, and this part is higher. Do you see that? So I can draw this as kind of from here do you see that? So as my base increases, now this is 3 to the power of x. If I have to do 3 to the power of, let's say 10 to the power of x, then how should it look like? Well, 10 to the power of must be very steep, but this point will never change. So it could be like going up like this, right? But on this side, it will be much lower. Do you understand? And it will approach x-axis, but never be there, okay? So this could be, let's say, something much higher, and we'll write this as 10 to the power of x. So as our power increases, the graph on the right-hand side becomes steeper and steeper, but on the left side becomes flatter and flatter. Do you see that? Closer and closer to the x-axis. So that's the basic nature of our graph. Now, coming back to our question. If we have b equals to 1, then how will the graph look like? If b is 1, what is 1 to the power of 0? 1. 1 to the power of 1? 1. 1 to the power of 2? Also 1. So for b equals to 1, we'll get a line like this. Do you see that? This is for b equals to 1. Do you see that? It is not an exponential line. It's just a straight line, which is y equals to 1. Do you see that? Therefore, it doesn't fit into our criteria of an exponential function. Exponential functions are those functions which increases very rapidly. Okay? Do you know how fast do they increase? Let's go back and look into our values once again. Now, you remember, when we were writing our values For linear function and quadratic function, the first difference was like what? First difference was increasing arithmetically by a number, right? And first difference was constant. For a quadratic function, the second difference was constant, and first difference was increasing by 1357. I hope you remember that. But here, you see the numbers, they are getting multiplied by a factor, correct? And their first difference actually is also a multiplication of the same factor. Let me write one more value and show it to you. Let's say we have 3 here. Then 3 to the power of 3 will be 27, correct? Now if I find the first difference here, so let me do here 3 minus 1 is 2, right? And how about 9 minus 3? 6. And how about 27 minus 9? Correct? 27 minus 10 is 17, but it is 1 less, so it will be 18. Okay. This is my first difference. Do you see the first difference increases by a factor of 3? 3 times 2 is 6, and 3 times 6 is 18. So it's higher, more steeper it is. It increases faster and faster. That is what we mean by exponential growth. It increases very, very fast or exponentially. Correct? So I hope you understand a couple of things from here. One, domain is all real numbers because x can take any value. Correct? Second, we have a horizontal asymptote here. Since as we approach minus infinity, we approach x-axis or y equals to 0, but it is never 0. Third, as we approach infinity, positive, y also approaches positive infinity. Okay? And one part, this is always increasing. Do you see that? It is always increasing. If we have base function which is greater than 0. Okay? Now, as I said, base function could be between 0 and 1, correct? If my base function is, let me take an example where base function is greater than 0 but less than 1. So let me take another example here, this time where b is greater than 0 but is less than 1. Okay, that means kind of half. Okay, so let's do that part. Let's take x values and let's say half to the power of x. Do you see that? Half to the power of x. So for 0, what do we have? Anything to the power of 0 is 1. If I take 1, then half to the power of 1 is half. Do you see that? And if I take 2, then half to the power of 2 will be 1 over 4. Correct? How about minus 1? When I take minus 1, this flips. It becomes 2, right? And for minus 2, so half to the power of minus 2 will give me 2 to the power of 2, which is 4, right? Now this particular graph, if you see and compare with this graph, do you see it has flipped? Do you see that? So basically that graph will be like, let me use a different ink here. Okay, so at this for half to the power of x. At 0 we have 1, but at 1 the value is half. It is not 1, it is half. So at 1 we have half of it. It comes here. At 2 it is 1 over 4, like this. Do you see that? And as we go further, we approach x-axis. Do you see that? Now for minus 1 we have 2. So at minus 1 we have a value here. And at minus 2 we have 4, like this. Do you see that? So it's kind of this function reflected on y-axis. Do you see that? So therefore our graph can be drawn like this. You see that? So this is the graph of half to the power of x. So if it is between 0 and 1, so the function becomes decreasing. And y-intercept is always 1. Do you see that? That is how your function is going to look. If I write 1 over 3 to the power of x, it will be as if 3 to the power of x is reflected on this axis. Exactly like this. You can make a table of values for that and check it for yourself. But the idea here is that if my value of b is between 0 and 1, then it is always a decreasing function, a kind of mirror image of its reciprocal, okay? That's how it is. Now, the first question, why b cannot be less than 0? So we have checked all the values, b between 0 and 1 and b, these were b greater than 1, right? So these were b greater than 1, right? So we checked both. But why b cannot be negative? Now, b cannot be negative, right? Why? Think like this. Let us say b is minus 2. Now, minus 2 to the power of 2 is how much? Minus 2 to the power of 2 is 4. And how about minus 2 to the power of 1? Minus 2 to the power of 1 is minus 2. And how about minus 2 to the power of 3? Minus 2 to the power of 3 is minus 8, right? And minus 2 to the power of 4 is how much? Is 16. So do you see, as the power 1, 2, 3, 4, it changes sign. That means we are sometimes here, sometimes there. Do you see that? For all odd powers, we will have negative thing, right? And for even, the function will be positive. So it's no more a continuous function, right? Do you see that? So the function will be like flipping like this, right? So it won't be a continuous function. So we cannot have b as negative powers, okay? So that's one reason about it. Okay, I hope you understand the exponential function and its basic properties. Does it have an x-intercept? In the basic form, it doesn't have. Does it have a y-intercept? Yes, always at 1, okay? By transforming this function, we can bring it down, up, left and right. We can have x-intercept also, correct? Well, so most important thing about this is, if b is between 0 and 1, it is always decreasing, and if b is greater than 1, it is always increasing, correct? Second, it always has a y-intercept at 1. Third, horizontal asymptote is y equals to 0. Perfect? And good points to check are close to 0. So minus 2, minus 1, 0, 1 and 2 are the points to be checked, right? So when we do transformation of these functions, we'll consider these points and the horizontal asymptote. Okay? Thank you.